Ooh, look at that well-drawn magnet. Oh, and I'm writing magnet next to it. That way you know. Ooh, magnets, plural. That is just one magnet. Anyway, magnets are magic. Just kidding. They're not. They're not magic, but they probably seem like magic to people who didn't understand science. Not like you. Anyway, so I made this stuff a while ago and haven't really watched it since. Oh, I'm drawing a magnet. Look at that. So that all magnets have a north end and a south end, and as some of you saw, magnets have field lines. So you maybe sprinkle some iron filings on them, and you saw shapes that sort of look like this. But sort of the question is why do they look like this? Oh, and I drew arrows on the magnetic field lines. Magnetic field lines run from the north end of the magnet to the south end of the magnet. And that is rule 1, apparently. And just like electric field lines, they never cross. And rule number 3, etc. Just like electric field lines, so you can just kind of go with that. And it's really all the same things applies. Twice as strong, twice as many field lines. And just like before, we'll go back to a rule 0, which says the field lines are determined by a tiny magnet. Which in our case we will always use a compass, because what a compass is really just a tiny magnet. And you can see it's a tiny mag and compass, very small parentheses. Good. Field lines, underlined, and these are rules. And obviously there are more rules because of the etc. But we get the idea. Okay, so here are some examples of some field lines that we may see. We can imagine that we have a north end and a south end pointing at each other, and the question may be something like, well, what did those field lines look like? Well, here's sort of the answer, but why is this the answer, or how? I don't know if how is the right. How do we determine it, I guess? All right, look, we can zoom in, like we get closer, and we can put in a tiny magnet, which is just a compass. All right, so we draw a compass here. And we would see which direction the compass would point. Well, compass being a tiny magnet, north is going to be attracted to south. So the compass is going to point not towards the north end, but it's going to point towards the south end. The north end of the compass is going to be attracted to the southern part of the magnet. All right, so then we draw our field line accordingly. So it points towards the south, right? And then we can kind of bold it in just a little bit, changing the... There we go. All right. So this is how we draw all of our field lines. We imagine a tiny magnet, just like the electric fields. We imagined a tiny positive test charge. Here we are imagining what would a tiny magnet do. So these ones curve because this is how the field line acts. And the field line acts this way because that is the way a compass put at these points acts. So a compass doesn't always point directly at a southern pole. It lines up in this particular fashion. So now we know how, and I guess I'll cross it out. And the answer is a tiny magnet, written very large and out of space, so compass will be written in small. So this is how we determine things. So let's take a look at how we would do it for a single bar magnet. What we would otherwise do with many compasses. So I'll write out, I'll read it as you read it. In what direction, read it together, the two of us, thank you. In what direction, okay, we ran out of time. So what direction would the compass point at point P? So to determine that, we could put a whole bunch of compasses all over the place, and we could draw them and draw them and draw them, and continually see what do they do. So we move a compass from one point to the other, from one point to the other, and eventually we get the idea that, well, we have a lot of places to put compasses, and we just kind of continue to draw them, and we see that we tend to have this trend, the trend that we already saw in our previous picture on that first page there. We have these lines that tend to loop around, and the direction that these lines have is given by not like in electric fields where the direction that the electric charge goes, but by the direction the compass points. In other words, the direction that north part of the compass points. All right, so in purple here we would have the answer to this question, which would point this way, sort of parallel to the magnet, which is not so intuitive. It does not point directly at the pole at this location. It's pointing in this sort of parallel, this sort of parallel place or phase or way or whatever. You get the idea. Okay, so this again, not necessarily an intuitive thing. So now we have all these questions. So what's up with Earth then? Maybe some of you are thinking like, well, as a compass points north, then what about the North Pole? Oh my gosh, so just zooming in on Santa there, and where is Santa? Okay, there's the Earth. Okay, so back to that question. Okay, look at those proportions. Okay, yeah, so there is North America, there is South America, named because they are, in the northern hemisphere, and probably other historical reasons, but we all know that history does not matter. Okay, so then here's the East Coast. I can write that in instead of just writing an E for some reason. And there's the West Coast again, writing small and for no reason. So we all understand these directions, and these are our geographic poles, our geographic directions, and we would write them in this way, oriented to this map of Earth, or this drawing of Earth, whatever you want to call it. And that's what we are used to. However, if we were to put a compass on the Earth, which we do, and what we now know about how compasses work and about how magnetic fields work, they are tiny magnets. All right, so let's zoom in here just a little bit. Yes, okay. So south attracts north. That's true. Good point, Phantom Pen. All right, so here we are zoomed in, and we're going to draw a tiny, tiny compass to imagine what. Okay, so there goes Central America. It's a tiny compass that covers basically a whole central portion. Anyway, so there is north, there is south, and what would the compass do? All right, well, it would point north, right? So that's why we call it north. But that means that it is pointing to a southern polarity, which means the northern part of our planet actually has a southern polarity, according to this tiny magnet, which is how we determine the magnetic field of something. Right? So now the question becomes, what else is wrong with the way we think about things? Anyway, so we can zoom back out and we can answer some of these questions. One of the questions above was, where does Santa live? Well, Santa obviously lives in the North Pole, but the North Pole is just not where you thought it was, right? Turns out it's all backwards. It's all wrong, right? North is not up there. South is not up there. Got to get rid of all these things, right? Well, east and west, I suppose, can stay. But in any event, our magnetic south is in the geographic northern hemisphere. Our magnetic north is in the geographic southern hemisphere, which we've all been looking in the wrong place then for Santa. He's actually right down here in the southern hemisphere at the North Pole. Your whole world is a lie. And that makes sense because in all those movies, who is Santa hanging around with down there? He's got his elves, right? He's got his reindeer, and he also has these guys. These little black guys that are always wearing tuxedos and only live in the southern hemisphere, aka known as penguins. You're welcome. I've now solved all of your childhood questions in this one video about magnets. Okay, let me just add the flipper on right there, and that's that. Okay, so there we go. Santa actually lives here. Your whole world is a lie. Hashtag Illuminati. Illuminati. Illuminati.